Swayam Prabha. Digital India. Educated India.
In continuation to the last lecture, in which I told you a very brief introduction to the mechanical type of advanced micromachining processes in general, and abrasive jet micromachining, ultrasonic micromachining, water jet micromachining, and abrasive water jet micromachining. I briefly explain the working principle of all these processes individually, some applications so that you can understand the capabilities of these processes, and I also gave the schematic diagram of the equipment of each of these processes. After that, I introduced the electric discharge micromachining and beam technology micromachining, in which I told you regarding the ion beam micromachining, electron beam micromachining, and other micromachining processes. All these processes are thermal processes, and I told you the working principle, applications, equipment, schematic diagram of electric discharge micromachining. Now, I am going to discuss wire electric discharge micromachining or wire electric discharge machining briefly. As you can see here, the electrical discharge machining wire cutting is a thermal mass reducing process that uses a continuously moving wire to remove material by means of rapid, controlled, repetitive spark discharges. Here emphasis is on the spark, not on the arc, as I mentioned in the earlier lecture. A dielectric fluid is used to flush the removed particles from the workpiece material, regulate the discharges, and keep the wire and workpiece under cool conditions. The wire and workpiece must be electrically conductive. This is the preliminary requirement of any wire EDM and EDMM process. Here you can see the microstructure made by wire EDM process. You can see this is the scale of 200 microns, and all these dimensions are less than or equal to 200 microns, and it is really difficult to make such kind of structure by other processes. And here is the working principle that we can understand of wire EDM process. Here is the dielectric being supplied through the nozzle. Here is the workpiece which is electrically conductive, and the wire is being pulled out from one of the pulleys and rolled up on the another pulley, and this is continuously moving, and there is a, as you can see in the side figure, there is a gap between the wire and the workpiece inner surface. So, that gap is known as inter-electrode gap, and this gap may be varying along the periphery of this wire, and so definitely the energy of each spark along the workpiece surface being machined will be varying, and you can see the slot size over here at the bottom, and this is the different one. So, depending upon your requirement you can control this slot width also. Now, applications of wire EDM process or wire EDMM process, you can clearly see this is the wire which has been fabricated with the help of wire EDM process. This is the another wire which has been fabricated by wire EDM process. The enlarged view of this wire is shown over here. As you can see, this wire is shown over here. So, the one end of the wire is having a kind of spherical shape, another is more or less straight side. So, the diameter of this spherical shape of wire is around 70 micrometer, while the wire straight sided wire or rest of the wire is around 40 micrometer, and this has been prepared by wire EDMM process. Micro touch probe manufactured using micro wire EDM turning process. So, you can see here, this is the enlarged view of this particular wire over here. Now, very important very commonly used process that is known as laser beam machining, and the miniature cutting or micro cutting by this particular process is known as laser beam micromachining. Laser beam micromachining examples are over here, as you will see. This is the laser beam setup, which consists of reflective end of the crystal. This is the laser crystal. This is the partially reflective end of the laser crystal through which the laser beam is coming out, and here is the lens. Lens is concentrating and focusing the laser beam at a particular location on the workpiece. The workpiece is there. Here there is no condition that workpiece should be electrically conductive or non-conductive and so on. And here is the power supply for producing the laser beam. Now, using this particular type of the laser beam, you can see here, this is the macro cutting, not really micro cutting, but macro cutting is there, and you can see 3.4 millimeter diameter hole has been cut, and this is the inclined hole that has been drilled in the 1 millimeter thick sheet. So, you can have different kind of the application of this particular process depending upon requirement. The basic principle I will just tell you about the laser beam micromachining. Here the full form of laser is light amplification by stimulated emission of radiation, that is the laser. Light energy of a particular frequency can be used to stimulate the electrons in an atom to emit additional light with exactly the same characteristics as the original stimulating light or stimulating source. Photon energy is proportional to frequency, but inversely proportional to the wavelength, and the photon stimulates the atom, causing it to emit an additional photon which identical characteristics to the stimulating photon, and as a result of this you have laser light. Laser beam micromachining setup is shown over here. You can see laser source, laser is coming from there, reflecting, then energy attenuator is there, and then again reflection, then beam homogenizer is there, and after reflection it comes to the lens, focusing lens, and it focuses the laser beam on a particular location on the workpiece. Now, you can see here there is target illuminator, machine vision, and then reflector is there, and here with the help of precision machining stage you can move this particular laser beam in x and y direction on the workpiece, so that you can exactly locate where the laser should machine the workpiece surface. So, this is a very interesting setup. Basics of laser beam micromachining. In micromachining process, generally ultra short pulse lasers are used. See, there are three kinds of laser that you can use: continuous laser, short pulse laser, and long pulse laser, and each type of laser has its merits and demerits and application. Some of them we will discuss in this lecture and in the following lecture later on. The material in the focal region is heated to melting temperature depending on laser intensity and pulse duration. As I have mentioned earlier also, that this is a thermal process, and here you are melting the workpiece material and later on evaporating also depending upon what is the temperature that has been attained by the workpiece. So, this process is accomplished by linear or non-linear absorption process. For opaque materials, linear absorption absorption long pulse lasers are used, and non-linear absorption ultra short pulse lasers are used. Properties of laser beam, as you can see, it is monochromatic, single wavelength is there, coherent, same phase relationship, directional, low divergence and very low divergence, beam spreads very little, intense, very high in density of usable photons is there. Now, the you have two types of lasers, basically gas lasers and solid state lasers. Here are the lasing medium, excimer laser is there, CO2 laser is there, and wavelength in each case is different, as you can see here. In case of excimer laser, it is 193 micrometer to 351 nanometer, 10 micrometer, this should be micrometer, and 1.064 micrometer. Now, when we are using long pulse lasers, there are certain problems that we come across. As you can see here, the long pulse laser is being used to drill a cavity in the workpiece surface. Now, this laser heat intensity is very high. So, any material that can be melted and even vaporized. So, here you can see this laser beam is hitting the workpiece surface over here. You have the melt zone of the workpiece material. This is the recast layer. Now, this recast layer is the one, the molten material when solidifies on the original workpiece surface, that is here on this side surface, then it is known as recast layer. Now, whatever material is removed from the workpiece surface, then it is removed and called as the debris, and it is in the molten state. And when the molten state material gets solidified, then you have small particles or chips kind of the thing, and they are known as debris or surface debris over there, and they get deposited on the top surface of the workpiece, and this is a big problem after you have completed the machining. Then you can see if there is a side structure, damage caused to the adjacent structure over here. If there is a structure near to the place where you are machining it, then that structure may get damaged, as you can clearly see over here. Now, surface ripples are also due to the shock waves are formed over there, as you can clearly see over here. So, heat is affecting the workpiece surface up to a certain depth, and that heat affected zone, as you can see over here, is also shown here. And since it is a thermal process, so temperature variation is there along the workpiece surface from the inner surface to the outer surface, and you can see micro cracks are formed over here as well as over here, and this creates a defect in the workpiece. So, and shock waves are also formed, as you can see over here. So, keeping this in view, in many applications short pulse laser beam is used rather than the long pulse laser beam. Now, in case of short pulse laser beam, as you can see over here, those kind of the problems which we just saw in case of long pulse laser beam machining, they are not encountered when you are using short pulse laser beam micro machining. As you can see, these are the short pulses over here, and when it is machining, when it has machined this particular cavity, now you do not find debris over here which you saw in case of long pulse laser beam micro machining. There is no plasma plume is here, and there is no heat affected zone over there, no shock wave is seen over there, no micro cracks are there, no heat transfer to the surrounding material, because heat whatever is generated over here, most of it is utilized in melting and vaporization of the workpiece material, and transfer of heat is minimal possible, and there is no damage caused to adjacent structure. This is the adjacent structure, and these are the ultra fast laser pulses and short pulses. So, we can see, especially in case of micro machining, ultra fast short pulse laser beam machining is better than long pulse laser beam micro machining or laser beam micro machining or laser beam machining. Now, here there are certain characteristics of laser beam machining processes, like mechanism of material removal. We have already seen melting and vaporization. Medium is normal atmosphere, no additional medium is there, and tool is high power laser beam itself is acting as the tool, and maximum material removal rate is just 5 millimeter cube per minute or so. It is quite low compared to other advanced micro machining processes. Specific power consumption is 1000 watts per cubic millimeter minute, and critical parameters are beam power intensity, beam diameter, and melting temperature, and materials application, all materials. Now, this can be used for almost all kind of material, except that those materials which have very high thermal conductivity and which have very high reflectivity, just like aluminum. It is very difficult to machine aluminum by this particular process, as well as very difficult to machine materials like copper. So, that one has to see carefully what material they are going to machine with this particular process. Shape application, you can make different kind of the shapes, that is not a big problem at all. Only thing is you have to have the relative motion between the laser beam and the workpiece being machined. Limitations: very high power consumption, cannot cut material with high heat conductivity and reflectivity. Just now I gave you the example of copper and aluminum. Effects of type of laser on machining characteristics, you can see here that different kind of the lasers are given over there, picosecond lasers and microsecond lasers. So, this will have different kind of the frequencies. Wavelengths are also different in both the cases, as you can see here. Minimum base short diameter that you can achieve is by picosecond laser is 1 micron, here you can achieve as 4 micron. Then vertical wall machine capability, aspect ratio you can achieve 2 and 2 in both cases. Tapered wall machine capabilities, aspect ratio is of 5 to 10, in this case also is 5 to 10. Deep hole drilling is variable in both cases. Machining accuracy plus minus 2 micron, it is not known over here in case of microsecond lasers, and average power of laser is up to 10 watts, here it can be as high as 100 watts, and materials machined may be metals, ceramics, polymers, glasses in case of picosecond lasers, and here also metals, ceramics, opaque glasses, etc. So, you can see different applications also of this particular process. Now, let us see, this is a micro cutting in a tungsten pin using 511 nanometer ND laser, and you can clearly see the sharpness of this cutting that has been made over here, and this has been done with the help of laser beam. Now, this is the another application over here, microfluidic device in silicon showing laser drilled by a hole and connecting channels. So, you can see this is the hole and this is the connecting channel, and they have been drilled and machined with the help of the laser beam micro machining process. So, you can see very fine cut over here, comparatively large hole being machined and connecting channel is being machined. Now, I do not have the hair, but you people, all of you have the hair, and if I ask you, can you write your name on the hair? Hardly any one of you will say yes, but if you see this picture, EXCIMER, excimer laser has been written on the human hair with the help of the excimer laser beam micro machining. So, micro machined letters on a single human hair. Note the clarity of the letters in the close-up view. You can see clearly the clarity of the laser in the bottom figure, and this is the full picture of that particular excimer laser. So, what I am trying to tell is that it has very versatile applications. Only thing is you have to choose the right kind of applications and the material. Now, there is another process called electron beam micromachining. Very interesting process. Again it is used mainly for the purpose of micro machining purposes or even nano machining purposes rather than macro or meso machining purposes. Now it works in much the same way as a cathode ray tube in a television. You can see over here, here is the cathode grid. Now electrons are emitting from there, anode is there attracting those electrons, and they are bifurcated, and this beam is coming over here. You have this magnetic lens over here, and this beam of electrons is concentrated on a particular location on the workpiece. Now see here it is written vacuum chamber. As I mentioned in the earlier lecture that mostly electron beam micromachining is performed in vacuum, but in some cases and in some applications you can perform it under the normal environmental conditions also. We will see what are the problems and advantages of performing that way. So cathode section generates the beam, anode section accelerates the beam, lens system converges and deflects the beam to the desired position, and electron beam machining process is shown over here. Why vacuum is required in beam, in electron beam micromachining? Now if you are not having the vacuum, then what will happen? You can see over here, this is the electron beam. Now when this electron beam is coming under the normal air, then what it will do, those electrons will hit the atoms in the air and their energy will get distributed in moving these atoms to different locations, and very small energy of these electrons is coming and hitting the workpiece. So you will not be able to get a right kind of machining with proper accuracy and tolerances. Now if vacuum is there, you can clearly see here that the whole beam of electrons is coming and hitting the workpiece surface, and in this particular case you can get much better machining accuracy and better quality of the machined surface. Here you can compare these two clearly, that here you will not get proper kind of the machining, but here you can get proper kind of machining. That is why I mentioned that normally electron beam micromachining and electron beam machining are performed under vacuum conditions rather than ambient air conditions. There are some process characteristics I will quickly tell you. The mechanism of material removal is melting and vaporization. I have not mentioned so far. What happens is electrons, although they are known to have almost a zero mass, very small mass each electron has, but when these very small mass electrons move with the velocity of light, close to the velocity of light, you can calculate what is going to be the kinetic energy of each electron, that is half mv square. With that kind of kinetic energy and millions of electrons, if they are hitting the workpiece, then a large amount of heat is generated, and because of that large amount of heat, the workpiece temperature rises to the melting temperature and even to the vaporizing temperature. So the mechanism of material removal in case of electron beam micromachining is melting and vaporization, or melting alone depending upon the conditions, and it is performed under the vacuum as I have shown to you in the earlier slide. Tool is beam of electron moving at a very high velocity, that itself acts as a cutting tool. Maximum material removal rate is 10 cubic millimeter per minute, maybe in special conditions only, or it may be normally lower than that. Specific power consumption is 450 watts per cubic millimeter minute, and critical parameters are accelerating voltage, beam current, beam diameter, work speed. Work speed is the speed relative to the electron beam, with the help of which you are creating different kind of the features on the workpiece being machined. And melting temperature of the workpiece is also very important, because it will decide the material removal rate and even the quality of the workpiece being machined. Material applications, it is applicable to all materials, conductive and non-conductive both, and I have already mentioned to you the constraint. Then shape applications, drilling fine holes, cutting contours in sheets, cutting narrow slots. And then limitations, very high specific energy consumption, necessity of vacuum and expensive machine. Definitely electron beam micromachining equipment are very expensive. Some of the data are there which have been collected from different books and journals, and you can see they have been able to machine materials like tungsten, stainless steel again, aluminum, alumina and quartz. And workpiece thicknesses are different over here, as you can see they range from 0.25 to 3 micrometer, and then you have the hole diameter that are being drilled over there in the sheet, and then drilling time taken in terms of the seconds, and accelerating voltage are different in different cases, and beam current in case of in milliampere are shown over here. So, using these data you can decide which kind of the equipment you should use for a particular application. Then electron beam cutting and workpiece thickness, same, it continues the same way for different materials and conditions, like tungsten is there, brass is there and so on. Now, pattern of holes drilled by electron beam machining, you can see over here, these are the holes drilled by electron beam micromachining process, and you can see here the size of the hole is 90 micrometer and hole density is 4000 holes per centimeter square. Workpiece is stainless steel, thickness of the sheet is 0.2 millimeter and time taken per hole is 10 microsecond. But if you go to the textile industry or food industries, they will say, oh, these are the very large size holes, they are not interested in so large size hole, they need still smaller holes. So, you can use this particular process for making even smaller holes smaller than this, and here you can see it is the 6 micron size holes that have been generated in the sheet, and hole density is 200,000 holes per centimeter square, thickness of the sheet is 0.12 millimeter and time taken is 2 microsecond per hole, and you can compare this with this 10 microsecond hole. It is quite less, and the dimensions of the hole are also smaller compared to the earlier one. So, depending upon the diameter of the electron beam, you can drill the holes of different dimensions. There are other applications which are shown over here, like welding of two dissimilar materials. Here electron beam has been used to weld the two dissimilar materials, because in general welding of two dissimilar materials is very difficult. So, batch of electron beam welded stainless steel to carbon steel is there. Electron beam welding precision, same 2 micrometer sheet 304L stainless steel to form a cylinder, that is being done over here, and such kind of typical applications you can use electron beam micromachining and electron beam welding as shown over here also. Principle of welding remains the same, electron beam is used, and when the electron beam is hitting the workpiece, maybe similar or dissimilar materials, it generates the heat and melting of the workpiece, both workpieces which are to be welded takes place, and if you allow them to cool down, the welding will take place. Here you have to be careful that you are not interested in vaporizing the workpiece material in case of micro welding. So, you have to choose the beam characteristics such that it does not vaporize any of the two materials, otherwise you will not get the proper micro welding. Now, you can see here different applications, this is for aluminum and other things, you can see welding has taken place. So, these are electron beam welding. Now, another process, very important process, is ion beam machining. Now, ion beam machining, as I mentioned to you earlier also, that normally it is kept in mechanical type of micromachining process, but in general authors have put it in the thermal process. That is why I have also put it in the same way. Mechanism of ion beam machining or ion beam micromachining: sputtering of knocking out atoms from the workpiece surface by the kinetic momentum transfer from incident ions to the target atoms. I will explain it briefly here. Now, you can see here, this is the incident ion. When this incident ion is hitting the atom over here on the top surface of the workpiece, it will be sputtered off, and this atom is removed from the top surface, and this ion is also sputtered off, and you can see both of them are going away from the workpiece surface. And this is an ideal condition where you have low energy ion beam and ideal case. In fact, theoretically it should be like this, but the energy of ion is much larger than the bonding energy of two atoms. That is why you will find that normally what happens, that ion hits the workpiece surface and more than one atoms, as you can see here, they are sputtered off from the top surface of the workpiece or couple of layers from the top surface of the workpiece, and the ion itself gets implanted below the top surface of the workpiece, which leads to the defect in the workpiece. And here, in place of removing atom by atom, it is removing cluster of atom, and you really do not get the kind of the accuracy and quality of the machined surface you expected. That is why you have to make the proper balance between the energy of the ion and bonding energy of the atom with surrounding atoms. So, at sufficiently high energy, the cascading events will penetrate more deeply into the solid. Several atoms or molecules will be ejected out, as you can see here, they are several atoms are ejected out, and the bombarding ion will become implanted deep within the material, and this bombarding ion is implanted deep within the material, and this is known as defect in the substrate. Typical material removal rate in ion beam machining, you can see removal rates by ion beam machining. Data argon ion beam 60 to 70 from normal, pressure is given over here, voltage is 6 kilovolt, current is 100 microampere, current density is like this. So, you can see material removal rate in terms of micrometer per hour, and this clearly tells you the kind of, you can see here the maximum material removal per hour, or the thickness that you are removing per hour is just 3 microns. So, it is extremely slow process, because 3 microns per hour is too slow. Hence, I told you in the beginning that it is basically used for nano machining rather than really micro machining, but under certain circumstances you can use it, but it is going to be very expensive process in that sense. Another group of micro machining processes was electrochemical and chemical micro machining processes. So, we have completed the basic principles and certain applications and set up schematic diagram of thermal micro machining processes. Now, let us discuss briefly the working principle of electrochemical micro machining processes and their different versions. Electrochemical machining principle is given over here, because electrochemical micro machining as well as electrochemical machining working principle remains the same. In this particular case, as you can see, tool is there which acts as a cathode, workpiece is there which acts as anode. And note it carefully that tool and workpiece material should be electrically conducting, otherwise it will not work. And you have the electrolyte over here. You can have different kind of the electrolytes, just like a acidic electrolyte, neutral electrolyte or basic electrolyte, depending upon what applications you are going to use for and what material you are going to machine. And when electrolysis takes place, it works on the Faraday's laws of electrolysis, and it is just reverse process of electroplating. In electroplating you are depositing the material, in machining you are removing the material. So, you have the hydroxyl ions, electrolyte is flowing at a very high speed, say 20 to 30 meter per second, and pressure normally is 2 to 35 kilogram per centimeter square is there, so that you can achieve this kind of the speed. And here are the metal ions, metal ion dissolution from the workpiece and hydroxyl generation at cathode. Now, another thing is, in this particular process, if you see carefully, hydrogen is generated which gets deposited, which gets adhered to the tool, and oxygen is generated at the workpiece surface, near to the workpiece surface, and metal hydroxides are there. What happens due to the reaction between the metallic ions and other constituents in the electrolyte, metal hydroxides are formed, and these hydroxides have to be removed from this particular inter-electrode gap as early as possible, otherwise your machining performance will get affected. And you can see here that this is the supply voltage. Supply voltage is normally ranging between 5 to 20 volts for the case of macro machining and meso machining. In case of micro machining, it is much lower, around 5 volt, less than 5 volt also is being used in case of micro machining. Now, suppose you are machining iron, then chemical reaction takes place, Fe plus 2 H2O, you get FeOH twice plus H2O, and this is metallic hydroxides that you will get over here, and hydrogen H2 is the gas. Then FeOH twice can further react with the water to H2O plus O2, and you get FeOH thrice. So, it can be ferrous hydroxide or it can be ferric hydroxide depending on certain conditions over there. And this is the simple schematic diagram for electrochemical machining, which can also be used for electrochemical micro machining. Now, you can see clearly that you have the pulse DC power supply. Normally DC power supply is used in case of ECM, but it has been found lately by the researchers that pulse DC power supply gives better performance, and especially in case of micro machining, it is only the pulse DC power supply which is being used by the users. Then you have the controller over there, tool driving unit is there. This is the tool is over here, and this is moving in the Z direction, and whatever you are having the shape of the tool and size of the tool at the bottom, the inverse replica of the same is produced on the workpiece. And you can see here is the electrolyte tank, this electrolyte is supplied, and this electrolyte is there inside the inter-electrode gap, that is the work tool, and this is the workpiece. So, this gap is known as inter-electrode gap, and that is being supplied by this, as you can see over here, this comes over like this and goes like this, same is true over here. And after it is used, it comes in the settling tank here, and from you have the filter over here, and from this filter it comes over, you have another filter over here, and cleaning of the electrolyte takes place, and after proper filtration and cleaning, you again send it to the electrolyte tank. Major characteristics of electrochemical micromachining: higher unit removal. This particular process, electrochemical machining, gives highest material removal rate as long as advanced machining processes are concerned, except plasma arc machining. So, in electrochemical micromachining also it is giving much higher machining rate compared to other thermal micromachining processes. Use of ecologically safe agent, this is very important. You have to use the ecologically safe agent, otherwise there are problems and people may have the resistance for using this particular process, because the fumes generated are non user friendly, and if these fumes are there surrounding to other equipment, then it may damage or corrode the other equipments also. So, you should always have exhaust in the machining chamber wherever you are using electrochemical machining and electrochemical micromachining setup, otherwise it will affect the human being as well as the equipment. It has faster rate of material removal rate is much higher, as I just mentioned, compared to other processes. Machining of chemically resistant materials, for example titanium, superalloy and stainless steel etc., is very much possible and it is easily done compared to the use of other processes. Now, here is the comparison which has been made between the electrochemical machining and electrochemical micromachining. This particular table has been taken from the work of Professor Vijay Bhattacharya from Jadavpur University, Kolkata, India. Now, you can see here the voltage is less than 10 volt in case of electrochemical micromachining compared to electrochemical machining. Current is less than 1 ampere, while here you can have 150 ampere to 10,000 ampere or more even. In case of ECM process or electrochemical machining or turbine blades, people have used as high as 40,000 ampere as the current, but in very special cases. Current density in case of ECM and micro ECM are very different from each other. Here power supply, normally you use DC power supply, but nowadays people are using pulse power supply also in case of ECM, but in micromachining you are using only pulse power supply. And frequency range are, you can have a frequency range of these pulse power supply different in both the cases depending upon the requirement. You have electrolyte flow as 10 to 60 meter per second, here less than 3 meter per second, because in this particular case you have to be careful as long as flow rate is concerned of the electrolyte, because tool is very small and weak. So, if your electrolyte flow rate is very high, it may break, damage or distort the tool, and which will affect the machining quality of the component, machine quality component. And electrolyte type salt solution you can use here in case of micromachining, natural salt solution or other dilute acid or alkali solution depending upon the requirement. Electrolyte temperature is quite high in both the cases, means 24 to 65 degree centigrade, and here it can be as high as 37 to 50 degree centigrade. And then electrolyte concentration also depends upon your requirement, but in case of micromachining you have lower concentration compared to the macro machining. And then you have the size of the tool, definitely in case of micromachining you have the micron size of the tool, and inter-electrode gap, as I mentioned earlier also, it is very low. It is inter-electrode gap here, it is 100 to 600 micrometer, while it is 5 to 50 micrometer. Normally it is within tens of micrometers rather than so large 50 micrometer. Operation is maskless, and maskless both can be done in case of micromachining. Machining rate is definitely low in case of micromachining compared to macromachining. And then you have the side gap I have just mentioned to you. Accuracy is reasonably good in case of micromachining, and you can have good surface finish, and low to moderate are the problems due to waste disposal or toxicity of the electrolyte, because it is not environment friendly and user friendly. Now, machining accuracy in ECM, you can see as shown in the figure, the bottom shape of the tool affects the machinability. Now, here is the cylindrical shape, here is the tapered cylindrical shape, and you can see in both the cases the shape of the cavity you have achieved. Here it is different quite compared to this particular shape, and it is due to the end of the tool as shown over here, and it is a straight sided end of the tool. When flat ended tool is used, the central part of the workpiece is non machined well because of insufficient supply of the electrolyte. Because this is not tapered, so you will not be able to get the enough supply of the electrolyte in the central part of the cavity being machined, and that is why you can see here the depth is much larger compared to this. Here the electrolyte will be passing through this part and reaching at the central part of the cavity being machined. On the other hand, the round ended tool shows good machinability due to the easiness of the electrolyte. Effect of pulse duration during electrochemical micromachining. SEM scanning electron microscope micrograph of 2 blind holes machined on a copper sheet using a 50 micrometer diameter platinum tool with a voltage of 1.5 volt, 5 microsecond pulse duration causes poor surface finish and inaccurate hole, as you can see over here. This is very poor surface, machined surface, and inaccuracy is there, and unmachined portions are also left in between, while but 100 nanosecond pulses significantly improve the surface finish and accuracy, as you can see here. You can compare this particular hole with this particular hole, both look very different from each other, and it is due to the type of the pulses used in these two different cases. Effects of machining parameters during ECMM process. You can see as the machining voltage is increasing, side gap is also changing, and it is increasing almost in all cases. They are using these conditions like electrolyte concentration, pulse, rectangular pulses are used, and feed rate is 0.144 millimeter per minute, and you can see this particular change in the side gap in all the 3 cases. Influence of machining voltage on unit removal rate. Now, you can see the kind of the applications this electrochemical micromachining has. Micro holes produced on titanium alloy cylindrical using jet electrochemical micromachining, and these are the holes which are of the micron size, and these are the exaggerated view of the holes. Production of high accuracy holes. Now, copper structure, you can see this kind of the structure being machined over here with the help of the electrochemical micromachining. Similar kind of the structure we saw when we used the abrasive jet micromachining process for that particular purpose, and copper structure machined into the copper sheet of an electronic circuit board. Now, you can see this particular type of the cavity produced, and this is the scale of 30 micrometer. Now, you can see titanium surface microstructure by through mask electrochemical micromachining produced long range accuracy and reproducibility of 30 micrometer cavities. This diameter of these cavities is 30 micrometer, and you can have another enlarged view of these cavities over here, and you can clearly appreciate that how smooth the surface you have obtained inside the cavities. So, there are various versions of electrochemical hole drilling processes. As you can see here, this process is known as shape tube electromachining. Here it is coated, insulated, insulation coating is there, and this is the hole inside the tool through which electrolyte is coming out. Then you have this capillary drilling over there. This is the electrolyte coming over here. This is working as the electrode, that is the cathode, and then you are able to machine this hole, but you can see the hump over here being machined. Then electro stream drilling is there, electrolyte stream is there, and it is acting as the cathode. This stream itself is acting as the cathode, and it is able to drill the cavity inside the workpiece. Workpiece is positive and this is negative. Then jet electro drilling is there. Now, this is electrolyte jet is there, and this itself is acting as the cathode, and this is the anode, and it is able to remove the material, and you can drill the hole or the cavity. And this is normal electrochemical drilling, where you can have the coated tool, and through the central hole in the tool you can supply the electrolyte, and you can see that the hole is being drilled more or less straight sided hole. If this tool is not coated externally, then you will get the tapered hole, and in many applications you may not accept the tapered hole, because you may require a straight sided hole, especially in case of cooling holes in turbine blades. Normally people need the straight sided hole or turbulated hole in many applications of the aerospace engineering. So, you can see here these are the various names which I have already told you: shape 2 electro drilling, chemical drilling, then electro stream drilling, and jet electrolytic drilling, and electrochemical drilling. So, this is the way I have already mentioned to you. Now, very important applications of this electrochemical micromachining is that deburring, adaptation of ECM to remove burrs or round sharp corners on holes in metal parts produced by conventional through hole drilling. As you can see here, these are the burrs which are formed due to the drilling process on this particular workpiece. Now, if you want to remove these burrs manually, it is going to take a lot of time and it becomes quite expensive also. So, what people have done, researchers have done, they have used electrochemical machining process for deburring purposes. So, you can see here, this is the cathode, here this is the cathode shown over here black color, and this is the burr, and between these two they are supplying the electrolyte. So, electrolytic reaction will take place, and this burr being the sharp, you will have here the highest current density, and this will quickly dissolve and you will get the deburred part. So, this is very important and very good applications of electrochemical micromachining or electrochemical micro deburring process. Electrochemical grinding process, again here this is a hybrid process, as I have mentioned to you that electrochemical machining and grinding, both these processes have been combined together, and the process hybrid, this process is known as electrochemical grinding process. Now, ECG is an electrolytic material removal process involving a negatively charged abrasive grinding wheel, a conductive fluid, that is electrolyte, and a positively charged workpiece. So, workpiece material depletes into the electrolyte solution. ECG is similar to electrochemical machining, except that the cathode is a specially constructed grinding wheel instead of a tool shaped like the contour to be machined. So, that grinding wheel, which is itself acts as a cutting tool, it is bonded with metals or electrically conducting material, and abrasive particles are embedded in the grinding wheel. As you can see over here, very simple schematic diagram is given. This is the grinding wheel, and these are the protruded abrasive particles embedded in the grinding wheel. So, when this grinding wheel is very close to the workpiece surface over here, and if you supply the electrolyte over here, then electrolytic dissolution will take place of the workpiece surface, as well as this abrasive particles will be in contact with the workpiece surface. So, they will also remove the material from the workpiece surface. So, the material is removed in two ways, mechanical way as well as electrochemical way. In mechanical way, abrasive particles are removing the material. In chemical way, electrolytic dissolution is taking place, as in case of ECM process. And you can see over here, workpiece is connected to the positive terminal, and tool is connected, that is the grinding wheel is connected to the negative terminal, and electrical connection is provided here, and this is the insulating bushing, so that this part, this grinding wheel shaft does not get in contact with the electrically conducting part of the grinding machine. That is why you are having this insulating bushings over here, and this is the electrode, that is this one, and you are supplying the electrolyte supply through this particular pipe. So, that will be coming here between the tool or the grinding wheel and the workpiece surface, and this is the DC power supply, as I have mentioned to you earlier also, that normally in ECM and ECG DC power supply is used, but people have found that pulse DC power supply can also be used, and it is quite useful. Now, this is certain feature or certain cavity that has been machined with the help of electrochemical grinding process on the inconel. Electrochemical grinding, let us see micro nano grinding processes. Process characteristics, it utilizes electrically conductive grinding wheels as we have seen in the earlier figure. It removes material by electrochemical decomposition and abrasive action by the abrasive particles which are embedded in the grinding wheel. It depletes workpiece materials and deposits them in electrolyte, and wheels wear extremely slowly because actual material being removed by the abrasive particle is very small. Large amount of material is being removed by electrolytic dissolution only. Workpieces are electrically conductive because electrically non-conductive workpieces cannot be machined. Now, applications are sharpening of cemented carbide cutting tools, grinding of surgical needles, other thin wall tubes and fragile parts. Advantages of this particular process are that it is chemical dissolution responsible for 95% of metal removal and abrasive action removes only 5%. That is why the regrinding process is very rarely needed for the grinding wheel, because wear and tear of the abrasive particle is minimal. Because machining is mostly by electrochemical action, grinding wheel lasts much longer time. It results much higher grinding ratio and less frequent dressing is required of the grinding wheel. Chemical machining is another version of this particular group, as I mentioned earlier, electrochemical machining and chemical machining. Now, electrochemical machining is based on the Faraday's laws of electrolysis, we will see later on. In chemical machining, immersion of chemical milling blanking is a chemical process that dissolves material from unmasked areas of metallic parts immersed in a tank of heated and agitated chemical reagents. The term blanking denotes small thin workpieces and milling indicates relatively large workpieces. Process characteristics, as you can see here, it is very simple. You have the workpiece over here, maskant is there. Maskant means it does not permit the chemical reaction to take place on the workpiece surface, and rest of the part where maskant is not there, you can clearly see the dissolution is taking place here as well as here. However, it is going inside the maskant also, so that this is known as overcut or it is inaccuracy that is being created in the machine workpiece. This is very interesting and very useful process, and you can see here that heater is there, heating you have to maintain the temperature of the chemical over here or agent over here, otherwise machining rate will vary according to the variation in the temperature. So, you should maintain the temperature, and second thing, whatever is dissolving here that is due to the chemical reaction, and it should not remain over on the machine cavity, otherwise your after a short period of time your machining rate will become almost 0. That is why you have the agitator. So, because of this agitator you keep removing the reaction products from these areas and mixing them up, and after certain time you have to replace it by the fresh agent, and this agent can also be used by after proper treatment. So, you can see here undercut and other things are shown over here on the certain workpieces. Now, parts are immersed in an acidic or basic chemical agent that you can see over here. This is the reagent over here, it can be chemical or acidic or basic, and masks protect areas from being chemically milled. These are the masks which are protecting this particular part of the workpiece from being machined. It produces close tolerances and fine details, as you can see over here, and this can be easily used for micromachining purposes, and it requires no finishing of the workpiece surface, because normally you get good surface finish. It requires no electric current as in case of electrochemical micromachining. I will stop here. Thank you very much.